All right, so does anybody want to hear about a little short story about AI?
Let's do it.
Like nobody wants to hear. No, I was yesterday because we were talking about this, and I have this somewhat funny idea about it. So I'm an electrical engineer and mostly a computer architect, and there's been times when I wrote a lot of software, but to be honest, I don't write AI software. I use AI, and then we make AI software go faster. And I run I'm CEO of a company called Tenstorrent. We have 1,000 people, probably 400 or 500 working on an AI software stack. And some of them really get it mathematically, and some of them just get how to build compilers and make levels of software. But when you run AI software, what you find out is that's all of AI software. Now of course you repeat this. There's a repeat statement. Repeat 10 to the 18th times that calculation. So at the fundamental level, AI software is pretty simple today, right? And then there's arguments about, does this have anything to do with how a brain works or not, right? And I think maybe it does, or maybe the actual calculation doesn't matter very much. But this is the core component of a matrix multiply. And generally speaking, a matrix multiply, so you draw a picture like this. You say, I want to multiply matrix A. Well, in this case, maybe it's B and C, but to get a new matrix. And basically, a matrix multiply says, so say this is I'm going to take a row and a column of the matrix multiply, and I take that guy times that guy plus that guy times that guy. So that's the times. So this is indexed by going across there by I, say, and this is indexed by J, going across there. And this is just accumulating the sums of this. And this gives you that piece of data. So this is just matrix multiply. You go look, there's all these pictures. Take a row times a column and get a piece of data. And then that piece of data is this row times that column. And that piece of data is this column times that row. And you slowly do it. And then you find out that the computation is something like what we call n cubed operations on n squared data. Right. So we do a lot. So you say, I got this data, and then I have this ratio of computation. So matrix multiplication is computationally intensive, turns out. Turns out, which is cool. And in an interesting way, it's the relationship between everything here and here, right? And then when people talk about AI today, they will mark one of these called weights and one of these called activations. Okay, and then that gives you a result, which is sort of the relationship of this to this. Matrix multiply is some level of universal function. You can build a mux out of it, an adder. This data here could have just ones on the diagonal. It could have a checkerboard pattern. It can be a lot of things. A lot of times when people look at big matrix multiplies, they'll say, there's a region with data, but it's all zeros, right? So, and you could say this is a learned relationship about, say, cats to fur, right? And this is a learned relationship about pointy eyes or something. But there's not really any relationship between pointy eyes and fur. So there's zeros. So who knows, right? So again, as a computer scientist, I think this is interesting. And then technically there's a pipeline, because then you multiply this times what's called like there's a whole bunch of words for it. Like there's sigmoid functions. There's, take the strength of this stuff, but you kind of get the activations for something else. And then, amazing. And then modern And then modern LLMs, there could be 100 layers of this. So it doesn't just feed back, it goes, right? And then there's a couple other features like embedding. How do you take a string of words and make them into a matrix so you can multiply it? Because we don't typically think that I see a dog and the dog is brown. So in AI, you can add those two sentences, right? I see a brown dog. Does that make sense? It's amazing, right? So it turns out in English language with normal spellings, you can't add those two sentences together. But with proper embeddings in a trained model, you can. You can also query it. You can say, what color was the dog you saw? It's a brown dog. Right. So AI is a wild thing. So the basics are unbelievable simple, and then the next thing I'm going to tell you is going to really screw up your brain.
Okay.
If you don't know how this works. But questions?
Oh, no, I was just going to say, is there some notion that's been discussed of maybe like concept space or something? I know Stephen Wolfram may have mentioned that at one point or another. I don't think it's assigned, but what I see there, like, all right, what's the concept? Something attribute to the dog, seeing a dog, to try to find where, I don't know, maybe it's just next token there.
Yeah, I'll try to give you a representation of this. But so, all right, so AI uses matrix multiplies and then some activation functions, which tells you like what's the strength of these relationships or something. And this is also trained. This is trained, and it's all good, clean fun. It has this computational intensity, which is high, and cubed on the data, which is amazing. That's why AI computers work. And then you can do amazing things like take things we think of as a sentence and put it in a space where you can manipulate it. Right? Does that make sense? All right, so then I'm going to say something about, so your brain is made out of coracle columns, which are little circles, and inside the coracle columns are, they call them macro columns and minor columns, right? And then these are in layers. I think a human brain averages 6. So the human brain has 20 billion neurons. I'm going to just do powers 10 because you guys are physicists and you get this stuff, so 10 to the 10th neurons, and there's something like 10 to the 6 cortical columns. So each one of these has 10 to the 4th neurons, right? And then wildly, this is all the neurons in each layer talk to each other. It looks like an all-to-all calculation. Super fun. And then if you look at the brain, it's this uniform mat of cortical columns. It's shockingly uniform. So your cerebral cortex, the lower brains are less uniform, but your cerebral cortex, where we think we do most of our thinking, and I would posit it evolved as a planning accelerator, because simple animals have 2 neurons, one for sensing the world and one for motor, like somatic and motor nervous system. And then as animals evolved, they started having, I want to get there and I want to get away from that, and then you have emotions around that. But at some point, the animal, they could say, if I do this and this and this, what happens? Or if I do this and this and what happens? And the animal who could plan the furthest in the future accurately won. Currently, that's us for 5 minutes. Okay. And then there's some really cool features of, so your average neuron has about 10 to the 5th connections. So everybody's seen that picture of a neuron where you got these really long things and there's all these little connections, dendrites and axioms. Okay. And if you just take the math of neurons, so the math of computation for a brain is something like 10, so a common number is 10 to the 18th operations per second, which is a relatively big number. And that's somewhat equal to 10 to the 10th times 100 hertz. That's how fast it fires. times 10 to the fifth. So that's 7, 17 times some mysterious number of operations that happens right there, 10. So every input that comes in, there's some number of local operations that does it. And then the neuron itself is summing up all the inputs, which is cool. So 10 to the 18th operation second, there's a brain. And then the really wild thing is the cortical column is about 0.1 teraflop, right? Teraflop. It just falls out of this math. And most of the computation, most of the connections are in the cortical column, but they have lots of connections adjacent, and then less further, and then less further. And then your neurons have a really wide speed range. So in the layers here, the neuron propagation is a fraction, it's like a millisecond or so. But the further you go, the speed stays pretty good, right? So the signal to your hand is really fast. So we have half a dozen methods to modulate nerve speed. So long nerves are really fast and short nerves are really slow. And that one thing that as a computer science says, that keeps you from getting multiple firing. So when this guy is thinking about shit and it says, go kick this, it wants to kick it together. It doesn't want to kick half of it with half the information, the other half, and then the whole thing and waste energy. And also the slow neurons are really low energy. So as your brain gets bigger, your brain is technically 1.3 meters of cortical column, 6 neurons thick, right? And we grew it just by having genes that say, make more cortical columns. So our brain architecture hasn't evolved for millions of years. Once mammals got cerebral cortexes, we grow just by, can the animal support that much computation? Does that make sense? Mm-hmm. So, all right. So then I'm building a computer, which is made out of arrays of tensor processors. So they say tensor, they could have said matrix, who cares, right? And our tensor processors are about 5 teraflops. And you could argue that's too big. But we also have to manage a lot of software to do it. So TPUs, this number is really big, like half a petaflop. So they made very large tensor processors. Some people have made small tensor processors. There's a trade-off because when I take a big matrix and I put it across this chip, so this chip has 140 tensor processors on it. So we lay the matrix out across things. And then all calculation means every piece of data has to get everywhere in the row or the column. Right? There's a power cost of moving the data. So if the tensor processor is too big, you put too much power in the tensor processor. If it's too small, you waste more power spreading it around. So neural architectures are super efficient about how they signal each other. So they've been able to tolerate smaller neural processors with more communication. I think our processor is pretty efficient of doing this. Does that make sense? So again, like I said, I don't know what this exact thing is. To me, it looks like a matrix multiply. It looks like low precision signals. Today we do, most of the math here is on 4 or 8-bit floating point, which seems like a ridiculous thing. People have done 1-bit, data types with calculations. And some people think the signal between neurons is a single bit. Some people think because of timing, because of how it transitions, it's multiple bits. But there's been a convergence. The kind of math you do in a tensor processor and the kind of math that you do in a stack of neurons is fairly simple. Similar, it's between 1 and a few bits. And the number of operations is also similar. It's with an order of magnitude of teraflops. There's trade-offs, right? And then neurons do a association, matrix multiply, and then an activation, which is what do we fire next, which is exactly what LLMs do. Okay.
Question, is the brain digital or analog?
It's mostly digital.
It's mostly digital?
It looks mostly digital. Because things fire. And firing is a discrete event.
Okay.
and it's semi-synchronous. You can see waves of computation happen, and the reason you want synchronous is you don't want to do half a calculation and then something else shows up, you do it, and then it inverts the calculation you just did, right? So, but it's not exactly synchronous, but there's a whole bunch of methods in the brain that make it look like it's firing in patterns. So it's mostly digital and mostly synchronous.
And as I understand, most of the signals in the brain with neurons have to do with frequency. They're like little tiny songs being sung to communicate between each other, as opposed to simply on or off or amplitude modulation.
Yeah, there's a lot of theories and papers about this, and I'm not an expert on that. I'm taking a relatively simple explanation of how firing leads to accumulation of results, but people do see lots of really cool behaviors in that. But also when neural networks are running, we see lots of really cool behaviors in the neural networks. So, and again, I think there's a lot of work to do. All right, so I'm now building a computer. So the human brain, so people, they think it's on the order of 10 to the 18th operations per second. Now there's people who think it's quantum or this or that, I don't know. We're getting really smart results with way less computation than that. And they think it's on the order of 100 trillion parameters. Yeah. So parameters is thinks of the number of weights in the brain. So the brain generically has
10 to the 11 parameters, 10 to the 18 operations
Yeah.
per second.
Yeah, and then I'm building a server which has about 10 to the
10 to the 7 difference.
so I'm building this fun computer which is 10 to the 16th operations, and it's 10 to the 10th data. So if you take this times 100, I'm building a computer, I'm building a 1 human operations per second computer, a 1 hops. Yay! I'll let you know it's powering on. It's a 1 hop computer. Human operations per second, 1 hops. I think that'll just make that capital. It's a 1 hop. So this is we're building this training computer, and it just happens to have 1 hops worth of computation.
Right now, right?
Yeah.
How long until it's?
Yeah, a couple months.
Wow.
This, by the way, is not that big. There's way bigger computers. They're just not coordinated, and depends how you do it. And then there's also a funny thing of so the modern training runs, they try to run them in 1 to 3 months for the really big models, and human beings mostly take 20 years to train. So, it's a different. So the training computers for modern AI are way bigger than human size, just for that reason. Because
I gotta give my respect for someone who's enough of a mad scientist to actually keep a human brain in a vat in their mad scientist lair.
Yeah, and by the way, this right now costs about it costs about $10 million, which, we're going to drive it down 100x in the next couple of years. So $100,000 to build a human brain's worth of computing. That takes a couple of years to train. It's, but there's a couple of wild side effects. All right, so I want to walk through 2 things that people assert. So LLMs are limited, and we don't have enough data. All right, so if you go on the internews, you'll see this. People love the argument. We can't do something, right? Wow, it's amazing. All right. I made a strong argument that we can't do something, but nobody checks. Like 5 minutes later when it's done, do you come out and apologize? No,
Everybody who
there's
argues
no
they can't do
apology
something
channel on
can't.
this stuff.
It's not really doing something.
Yeah, it's a funny thing.
Yeah.
All right, so these are very common statements. We can't get to artificial intelligence with LLMs because they're too simple. And what I tried to walk through for part A was the core part of this is simple, right? The core part of how neurons fire and talk to each other is really simple and curiously related in terms of operations per second, number of exchanges of information, data type. Like it's pretty interesting, right? Now we don't train LLMs today like brains are trained. As a matter of fact, it's not exactly clear how a brain is trained, right? Which is a curious phenomenon, given that the what we call the forward pass of computation doesn't look similar, but the backward pass doesn't. And I'll just give you a picture. So LLM we can think of as a bunch of, let's see, I'll just draw boxes. Let's imagine each one of these is a pile of this. And then we put some input in, right? And you can think of as inside the box there are the weights and then activation. So each block has weights or what we call parameters, right? And the human has 100 trillion of these, which is a fairly big number, but not radically big. It's a couple of disk drives these days, right? And then the way these are trained today is called guess the blank. So imagine you put the sentence, I see a dog. I see a dog. And then what comes out of here is noise. So we start the training with all the weights set to noise, right? And then we do one more clever trick, which is where they call guess the blank. We don't put that word in, and we are asking this to produce the word see. And then we subtract what we got from what we're looking for, right? And that's the difference. And then we simply push the difference back through the training. And this is where Hinton and a couple of geniuses figured out something called gradient descent. So these could be very large matrices, say 2,000 by 2,000. This might be 100 deep, right? That's a lot of shit, right? And so what you don't want to do is just take the whole difference, which you can just calculate, it's just ASCII, right? And just drop it there. We want to do some calculations on why was this wrong compared to the difference and why was this wrong. So gradient descent is a mathematical formula, and I'm sure if you go into Wolfram Alpha.
Different weights
What's
waiting for. How do they know what they're waiting for?
Generically, you don't care.
Oh, you don't care.
I got no. So when they first started doing what's called convolutional models, so what's called CNN, convolutional neural network versus LLM, large language models. At the bottom, one uses fundamentally convolution as a primitive. The other uses matrix multiply as a primitive. In the layers, like say you were looking for cats in an image, some of the layers would look like they had trained for pointy ears or round eyes. Like you can see, and the image you put in is segmented, and there's some clever tricks to get this to train fast. But an LLM and your brain look unbelievably generic, right? And mathematically, setting this up to kind of allocate stuff different ways can speed up training. And there's a current idea which is called mixture of experts. So there's a core model, and then there's a bunch of different models around it. And somewhere in the input stage, they said, this is about politics, or this is about math, or this is about horses. And then it's sort of generically training these things, but they're only training, like this is the horse expert and the politics and the math and the, music, right? So it's a little direction so that, but there's, people are going through this, is this really better or just easier to train or, because sometimes you want to know about the relationship between horses and music. It's kind of complicated. All right.
And how do you actually break it up efficiently?
Yeah. And then you can do the same thing with a picture. So you have a picture, and there's a boy, and there's a dog, a cow. Right. And then you put the picture through the pipeline, and you put a blank in, and you guess the blank. Right. Isn't that cool?
Is that how we get a Minotaur?
What?
Is that how we get a Minotaur?
Right. And then you just do the same thing.
Oh, okay. Oh, so for a page, it's basically just filling in what it should be given the parameters.
So
All
right, so what the hell is happening here? All right, so then it turns out for these large models, the more data you give it. So there's two things. If you have way more data than parameters, the parameters get what's called overfitted. They can only see what the data set says, right? And there's a couple of really good curves which says, there's this line, and then people can't get past the line, and the line is the line is the product of computation times data times parameters. So as models have gotten smarter, right, we get more data, we get more parameters, right? So if you have a gigabyte of data, a terabyte of parameters is too many, but a megabyte of parameters is too few. It'll be overfitted, right?
This is starting to explain why, because allegedly.
And I'm about to say this is bullshit in a second, so just don't get too attached to it.
Oh no!
But
allegedly people were paying like Wolfram Research to just buy just a whole bunch of just random math that it's like we actually do the computation here, but they were buying it to help train the things.
Yeah.
Which I think even Stephen Wolfram's like, they want to give us money for just a whole bunch of gobbledygook. Fine.
Yes. Well, by the way, they say the unreasonable effectiveness of math, the unreasonable effectiveness of this equation is driving the modern AI. So the data they're buying isn't gobbledygook.
I was going to say I used
right.
the wrong.
And you can also do stuff like you can take a whole bunch of, let's say, input questions, like can you do this math, or can you recognize a dog, or right? And then you look at the error rates of different things, right? And then imagine there's a mathematical space where you could study that and say, I need to shore up my mathematical space with the following things that Wolfram Alpha can easily produce. So you send this packet of requests to Wolfram Alpha, and he goes, what the fuck, this is bullshit. It's actually exactly what the model needs to reduce the error rate on that stuff. Right. The same with images. Like the internet is full of boobs, right? Yeah. So the models are overtrained with boobs, and image generators like to put boobs on everything, right? So, but in the mathematical space, boobs have a certain, attractive force, and you can compensate that.
So you do.
Yeah, it's not my fault. I'm literally just an observer here, right? Okay, and then here's a theory, and I've talked to a few computer scientists. Imagine there's a weight in here which seems to really be effective at connecting a bunch of things, right? So then think about human language, right? We don't have words for everything. We have words for the things that are pertinent to have words for. And an efficient language has words for a whole bunch of things that we use all the time. But if I want to describe the corner of your backyard where the grass has a clump of dried grass on it, there's no word for that. I just describe it, right? Yeah. So then if you go through a modern language model trained on language, you can actually dump out the words, right? So you can train a language model with images, and then dump out the names of all the things in the images. And then you can build a translator from the language model's definition of those words to the English language words. So you can naturally train this to give you a dictionary, and then with some kind of function, make a translator to English. Right? So you ask, is there representational space? Yeah, because the simple models only ever get to describing cat and dog and chair and run and walk. But as you add more layers, you start to see association, affiliation, friendliness, training, pedigree, right? Right? And as you do more of this, so imagine there's a computational space, which as you go up, you got objects and actions and associations, and who the hell knows what we call, what we said yesterday. It's like the kind of research you're doing is a high level, metaphorical space. I'm taking the associations of math, physics, measurements, computation, and putting them together, which is not, like we have some simple equations like E equals MC squared, but they don't mean anything to most people. For that to mean something, you have to have a higher associational space. And as you go in the higher associational space, there's actually less words.
Really?
So down here, all the objects in our life have names. All the actions have names.
I see.
Right.
But
in the higher stuff, people write whole books describing the political transformation of, post-war Germany in relationship to the economics of the Turkish immigration wave. Like, there's no word for that.
Have you guys
Actually, in German, there might be a word.
have you guys been using any category theory to try to?
I don't do this. I'm just reporting.
Okay.
I'm a reporter.
No. Just the way you're labeling it, I think that.
No. I'm very intrigued by it. Okay. So this is a well-known thing. So I think people will say this number is between 10 to the 16th and 10 to the 24th. Whatever. I think that's a reasonable answer because I can count neurons. I can see them fire. I see their connections. I don't need to make it more complicated. I don't need quantum to explain intelligence. I think these models are pretty smart. Now, I think the way we train them is crazy, right? So then I did an experiment. So I have two daughters, and when they were 16 and 17, I taught them to drive. And one of them, I played hundreds of millions of hours of video to train her neural network. And the other one, I gave her a list of 20 rules and let her drive a car for half an hour. And they both achieved driving pretty good. No, actually, I didn't force my daughter. I threatened her. I told Catherine, you watch a lot of video already. Would you mind watching 100? So the way they train cars to drive today is they play them 100 hours of video. And that's part of the problem is, let's imagine this is, an actual intelligent model, right? And that's the computation. This is the computational ability of a car computer, right? So there's two ways to teach you to drive. One is you put all the data for driving into a car computer set of weights, which is really it can't do anything besides drive a car. It doesn't theorize about why that person's not putting their turn signal on, yada, yada, yada. The other is if you have artificial intelligence and 20 rules in a 20-minute practice, you can learn to drive a car, right? So there's two ways to do it. So AGI is really effective, right? But the computer, you'd have to put in a car to drive, like my daughter's learned to drive, costs $10 million, and it's a megawatt. So that doesn't fit in the car. So we made the expedient choice of putting relatively dumb computers that are trained with massive amounts of data, right?
So you're using AGI as a generalized term there.
Yeah.
For something
I'm saying something intelligent as, one of us, maybe. All right. So here's the funny thing. So LLMs are limited, but they're not limited because of the kind of computation they do. Because that's what we do. There is this weird thing of we know how to train these models, but we don't exactly know how backprop works, right? And because what you see in the brain is this clusters of things. Every once in a while it does stuff, maybe like backprop. And we dream at night where we reformat all our data. And by the way, modern computers, when you're talking to the ChatGPT, has 3 levels of memory, right? You can think of it as the model weights or parameters. That's what's baked into the neural network. And then it has let's say a midterm memory, and then it has your prompt, right? So the way we get AI, LLMs to feel intelligent and interactive is we give them a big prompt and we say, so the prompt says, be intelligent, answer questions like this, when necessary, go look up Goethe for an opinion. Like the prompts are pretty big. And then as you're talking to it, they can have really big context, like 100 million tokens, like 1 million tokens. We're not up to 100 million yet. Those get factored down because that's computationally ineffective to take everything you're saying and redo it. So it's reducing it. And then at some point, what some people think is the prompt gets factored into this kind of midterm memory. And then when you dream, some of it gets incorporated into the weights. Because what you do with weights is really fast, and everybody knows this. When somebody explains to you how to play tennis and you go out and you go, all right, put my hand up, no, put my hand like this, and you're thinking about it, you play shit tennis. And you do that every day for 2 hours for 6 weeks, and you've turned it into, we say muscle memory, there's no muscle memory. You've turned it into hard, coding in your neural network.
Learning to interface with the
Yeah.
environment.
And in my process of learning in school, I'm a dyslexic slow learner. I put it in early and repeated it a lot. So by the time I went to do a test, I had calculus here. I had smart friends that could do you could explain shit to them, and they could do it from there. I couldn't do it. Then they would say, I forgot the next day. I never forgot most of it until recently. And I had to admit I can't do calculus anymore. But okay, so what the hell is going on here? So this is really wild. So we have an unsolved problem, and we don't know how to train human brains. Now there's people doing really fun experiments, which is, imagine here you have a model that predicts what the error is going to be, right? So people have done this and had some progress, but it's still not as computationally efficient. It's just brute forcing the shit out of it. But you can start to basically build these guys as more independent entities, right? And there's one idea that was pursued is, what if the brain doesn't propagate all the way back, but it's generating outputs, but also it's generating what it thinks is going to happen, and it updates those things. Because your brain is very good at doing parallel trials. Your brain is a trial machine. I'm imagining what the future is going to be like. If I'm right, I survive, and if I don't, I won't. And I can do multiple of those in parallel. And amazingly, while that's happening, your brain has a linear narrative. And the reason for that is that's a half a second behind your computation. So the thoughts in your brain aren't real. Well, they're behind the narrative. They're instructive for future training and,
I'd say it's a little bit of a lag.
yeah. But your brain is doing massive parallel experiments, and it's filtering up, and you actually mostly do only one thing. Every once in a while you see somebody did it, because 3 things all said, go left, go right, stand still, and then you freeze. Right. Okay, so what the hell is going on here? So I'm going to give you some math. Sorry. All right. So modern AI is what's called, I'm going to call this data. But technically, it's from that framework. Computation plus data plus parameters gives us the modern intelligence. And I'm going to say that humans are computationally intelligent plus experiments.
Plus experience.
Experiments. Right.
What do you mean by experiments?
So, will this fall when I drop it?
I'm pretty sure it is, yeah.
Well, we try it. All kids.
Yeah.
They don't just
Yeah.
ask mom and daddy.
All right, so how many bits of information came from that experiment? 1. You don't need the image of it falling. So we're always doing this. I have this idea about this equation. Will it amount to anything? You do a whole bunch of equations. Your brain is doing 10 to 100 times more samples of that. And then you say, wow, 1.1 times 10 to the minus 52 is curiously related to this other 1.1 times. That's only one bit of information. All right, so here's the math. I have to take this. I only have two hands. All right. So humans take 20 years to train. All right. And in 20 years, you're awake for 73,000 hours. All right. And I would say you get 1 to 10, let's say 10 interesting images per hour. So I'm going to call that 100,000. So I think you see between 1 and 10 million images. I think you also get to see 10 to 100 million hours of video. And by video, I mean stuff coming in. So video is a relationship between images from which you can extract all of physics, right, for example, right? Now, this is kind of wild. Humans talk at 150 per minute. Some slower, some faster. I met a guy named Butler Lamson who famously spoke at 0.5 Lamson. Talk really fast. But the joke was his wife spoke at 1 Lamson. He only spoke at half a Lamson. Yeah. All right. So if you get 4 hours a day, but you're doing half the talking, in 20 years, that's only 500K words. All right. This is a trivial amount of information. And I will point out blind people can achieve intelligence, which means with 500,000 words, you can achieve intelligence. That's why my daughter was able to drive a car without watching 100 million hours of video. She already achieved intelligence. Intelligence is a generally useful tool, right?
Yeah, no kidding.
So, all right, so what's going on here? So we have a couple of funny problems. We know how to train a language model to be pretty smart. People tell me all the time, but Jim, it's not creative, a little randomness in it. I had to write some movie scripts which were much more interesting than Star Wars. It wasn't really hard. It can't discover mathematical things. Well, there's a general rule which is if AI can do it, it's not intelligence. So we thought we needed AI to play chess. We played chess, we didn't need it. We needed to play Go, we play Go, we don't need it. We needed to categorize images better than humans. It did that. We needed to be a better lawyer than all the law firms on the planet. It did that. But people go, well, that's not real intelligence. Real intelligence is the thing it can't do this minute, which is changing every
But they think that what they're doing
minute. And there's a new pundit, and Jan LeCun, he's like, LLMs will never get there. And he has all this stuff about why matrix multiply is insufficient. And I think, who knows? I don't know. Maybe, I doubt it's magic. All right, so humans become intelligent almost entirely by computation. But not entirely. You need some feedback. Now, it could be possible there's a kind of intelligence that could happen without any inputs. But just think of how many inputs a blind person got. Like how many falsifications did they get as they were growing? And I think being blind can slow down your intelligence rate, but not your peak apparently, because there's plenty of very smart blind from birth people. And as a matter of fact, they also are less distracted by the 100 million hours of it, whatever. So, I don't know. So it's a trade-off. So what the hell is happening?
Good question.
So we generate, just think about, you said you can't see an object you've never seen before, but in fact, the brain is a blank slate when the baby's born, and it's getting all kinds of information in that it's never seen before, right? So what happens is it goes in and it produces that,
Yeah.
right? And then it starts going in its training thing. So it starts remembering the raw inputs, essentially. So then, every day it sees this, and then it sees this. And this was an undifferentiated pixel field. But suddenly, this is a differentiated pixel field, because some of these pixels look just like that, and some of them don't. Right? So it's just started to achieve object recognition. So it's just literally processing. So it's not what it hasn't seen before. I'm just thinking about this from your comment. It's generating memories of actually what it's seen, but it's uninterpreted.
Yeah.
So the boot process, a friend of mine really likes the word the boot process. The boot process is you have this data, similar with words. You have just signals wiggling in your ears, and you're recording all of it. And the brain is going, I'm just doing it's Lagos all over again. I am doing a massive pattern search for things I've heard before. So the first time mommy says, hello, honey, that's just frequencies, right? It got recorded. Right? So every day she says, hello, honey, and it starts going, there's a gap and a hi and a hello and a honey, right? And it starts differentiating those out of the noise. And neural networks are super good at this. Did I see this before? You go through memory, you run it through this, and with very little, you start to differentiate objects, and then objects move. And then somebody associates object with the word chair. And the boot process, you can see in the kids, they first are just wiggling around, and then they kind of wiggle over, and they wiggle over, and then you can literally see them twitching all their nerves. So they got robot training algorithms that says, put an AI model in a robot and just let it wiggle. They do this accelerated in simulation, and a week later it's walking around with no input whatsoever.
From just its own experience and
Wiggling,
iterating
yeah.
through it.
And there's ways to accelerate it. You can give it videos of humans walking around and say, generic instruction, right? So we're computationally intelligent in the sense that we start with a pretty blank slate. We start the boot process by trying to find and recognize things we've seen before, because that starts to give structure to the world. Why does it work this way? I don't know. It's super useful. It predicts reality. We have a mental model of reality. We can plan ahead. Made us super successful. I'm not a why guy. I'm a how. You know what? Right? And the amount of information you have to do is very small. Stunningly small. Right? So, I have a question. Yes?
What is the impact of surprise?
Surprise? Oh, it's great. You remember, it's like surprises are one of the best things that ever happens to you, right? Like I can remember a whole bunch of surprises, right? Because think of when you get an error signal, like you see black chair, and then there's a blue chair, and I thought chairs were black. Well, so you've disassociated. So it's a little surprise. Where, when your girlfriend cheats on you, it's a big surprise because you thought you were going to get married and have a family, and she's, banging the pool boy, right? So the size of the surprise at some level is how much does that have to propagate into your weights?
I was going to say, a surprise I would assume would give it to a greater weight because it was not what you would expect.
Yeah, like your talk yesterday, you said, here's 5 parameters, they're only accurate to 4 or 5 digits. I was like, what the fuck? I didn't think about anything else all day. So now I was talking, I was listening, I was trying to pay attention, but part of my brain was going, that's crazy. Oh, that explains this phenomenon, this phenomenon, this phenomenon, this phenomenon. It explains why these guys are on such thin ice. Because, engineers get trained if it's 1.3 plus or minus 10%. You don't do a calculation and write down 1.47583. The plus or minus 10% define how good that was. Like, so when you divide 1 by 3 in engineering school, it's a trick question, right? You learn, equals what? 0.3, 0.33, 0.34, What?
Depends on who you ask.
Well, no, it depends on how these were defined. And smart engineering students, so I was in a class where there was a thing, and it was like this, and the student said, "Professor, what's the precision of the inputs?" And he goes, "That's actually the," he told the whole class, "All right, everybody just heard the answer," right? Because the correct answer was, "I don't know." Because you didn't tell me this, right? So anyway, it's a funny, right? So I think surprise is a beautiful thing, and you can see the depth of the surprise based on how much computation it takes to fix it, right? I'm a decision tree guy. So in engineering, you reach your first decision and then your next decision, right? And then say you're pursuing this path, and then you find out something there, it doesn't work. Most people will say, well, let's revisit that decision. They don't want to revisit that one, and that one, and that one, and that one, because statistically, the problem, if this was pretty robust, it's 80% here, and 10% there, and 5% there, and 2% there, and 0.1% there. But if that's the one you have to revisit, you have to revisit it. Otherwise, you're fucked. Right? So surprise is partly the depth of the tree. Anyway, all right. So I think I wanted to show two things. The current limitation of LLMs is not about the computational structure. The current limitations of LLMs is they're data intelligent with a relatively simple, brilliant, but simple, sort of once you know the answer. E equals MC squared is kind of cool when you think about it. It's also ironic because we don't know E is or M or why C is C. So it's like the most famous equation is based on 3 undefineds, but whatever, not my problem, right? So we have this simple training method. Humans have another training method we don't understand, and they achieve intelligence with a trivial amount of data. So, and we are building computers which have the operations and the parameters. So my prediction is AI is going to accelerate. Right. So we falsified the LLM limit. Wrong. We falsified the data limit. Wrong. AI will accelerate. And it accelerates for a funny reason. If you want to teach 1 million people the same thing, you have to teach all of them. If you want to teach 1 million AIs the same thing, you just copy the weights. So, all right, that was my talk. Any questions?
So when you're saying this, when you were going over like the human inputs and everything, and if we're quote unquote able to train with so much less data, why might that be the case, or is that like just?
It's partly the human training method is unknown, right? And then humans take 20 years to train, which is and again, when the kids start training, they're looking at undifferentiated image and language information. By the time they get to school, you can tell the kids to sit in a chair and write down simple numbers. By the time they get to college, you can say write an essay on post-war German economic impact of Turkish migration, right? Those words are loaded. Like computer scientists tend to count like data sets in terms of bytes. Imagine a volcano exploding in Maui. It's a terabyte of information. Well, to you it is. Maybe if you haven't been to Maui, it's less information. But I've been there. I can visualize the volcano. I just did. It's an island in the sea. It's a volcano. It's 10,000 feet high now. It's been eroded 50%. It's unbelievable. There's been 25 landslides bigger than a cubic kilometer into the ocean to create tidal waves through 500 feet high.
Wow.
Like, so, yeah. But encoded in those words, for you was one thing. For me was a different thing. For you was a different thing, right? But it's really dense. So what happens when you train? The density of the communication just keeps going up and up.
Because all of our weights would be a little bit different.
Yeah, and at some level, when you start training, you're getting, pixels. You just think of the pipeline. The modern LLMs are exchanging concepts that are really high. and they are meaningful to the LLMs.
What else do you see emerging as it continues to accelerate? What's the next emergent properties that we might think about?
Well, it's sort of weirdly good. Like humans can famously remember like 7 digits in their head, and so many things. And if you want to like actually go research, like how does your equation talk to the other ones, whereas AI models can, you have 1 million digits in your head and do associations. So it's today it's super powerful on a whole bunch of dimensions like that. People say it's not going to be creative. Most people aren't creative. People say, what's the world going to be like if AI is smarter than us? Well, what's the world like for the 99% of the world that's not as smart as the 1%? I don't know. Like people say, I gave this talk on, there's an accelerating curve, right? But everybody's familiar with what's called diminishing returns. So what the hell is going on? Well, an accelerating curve is actually a stack of diminishing return curves. And so humans are on a whole bunch of diminishing return curves. Like most people believe we're running out of energy and natural resources, and we're overpopulated and we're polluting the planet. Like these are all nonsense. Like there's unlimited atoms and energy, and most of the planet's empty, and it's actually in better shape than it was 50 years ago. Now, it's also generating new, toxic food, and there's real problems, but they all have their things, and everybody in the news likes to talk about Moore's law is dead, which is essentially the accelerating return curve on transistor density. So I worked at Intel, which is the Moore's law company, and most of the engineers believe we were hitting limits. So I did a talk about a path of 50 to 100x more transistors. And some people got it, and some people are like, but Jim, you don't understand. The machine we bought from so-and-so that I don't understand has a limit. Yeah, rotary phones had a limit, right? You could only dial so fast because of the springtime, right? Push buttons were faster, touch screens were faster, and now nobody knows their own phone number, right? Like it's, so we go through these transformations. So transformations that are way bigger than what we can imagine are hard to imagine.
The one thing when I look at this is everybody doing kind of their own one-off implementation, so that let's say with OpenAI trains, but it's trying to give Claude new knowledge. They're incompatible data structures that are being used. Is there any standards?
The standard right now is the English language, which is unbelievably expressive.
Okay.
Yeah, so we don't need, English is really powerful, right? So you can also do images, you also can do math. So math is really powerful, images is really powerful, English language. Language, again, technically, it's the label of an interesting weight or a collection of weights or associations. So language, is, people keep looking for the deep structural language in neurology and stuff. And I think the deep structural language actually exists in information space. Like in the reality we live in on rock balls like Earth with air and animals, language is in that, is the namespace of the things in it and the actions in it and relationships between them.
I can't get down lower than language, because I thought about before, I'm like, oh, what is the basis? Normal response. Oh, it's obviously physics, because it's. But then you're like, well, physics, we are representing it with math.
Yeah.
Then math is technically
Yeah.
language.
Well, just think, the number of words getting up to, here somewhere is, 100 or a couple 100,000 if you go into technical dictionaries. It could be AIs are going to create languages with trillions of words, because it's economic. It's now it could be. It doesn't really matter that much, because you can, I can create a massive data exchange just by saying volcano and Maui exploded, right? So it could be, this is, there's a whole bunch of arguments about how to compress and encrypt or, exchange information.
Well, even 100,000 words is just a combinatorics. It's just.
Yeah. Like there's a thing called a branch predictor in a computer, which says when you're running the program, which way does the branch go, right? And then And then we had this tracing environment, so trace where the program goes, so we could study things like branch prediction. And it turns out when I ran the traces of the programs through a compressor like gzip, the compression ratio was proportional to predictability of the branches in the thing, right? So a program when it runs, some branches are like loop for 10 times. You know everything about it. The program says branch 10 times and then fall through. There's no information in the branch, right? But load this piece of unknown data from a database and then test whether the bottom 4 bits are 1. You don't know anything about it, and that branch is fundamentally unpredictable. Now, if the database is of middle-aged people from Ohio, they'll have a cluster of distributions of data about them. So that branch may be 80% predictable, right? So information theory is, applicable to all kinds of stuff. So whether the AIs will come up with better languages or use English and images in math, like math is a really good way to describe certain things. Like you go crazy defining all the points on an exponential curve, but you can say, why, that's pretty economical. And I presume the AIs are going to be really good at discovering new economical.
I see them needing the new changes. I mean, how languages evolve. I see AI as being a big effect now on how English continues to evolve.
Yeah. And then we will interface to the level of English. And the AI will suss you out really quick and say, are you at this level, or this level, and speak to you appropriately.
So just so I'm understanding part of this point correctly, for a computationally intelligent machine, it doesn't really matter what the specific channels are of those inputs. They'll all reach toward the same underlying structures.
It could be. Yeah, I don't know.
But
yeah, my point is
words to get there. Or you could use images, or
yeah,
you could use sound, or
yes,
sensations of some sort.
And there's a theory which is you could train a computer with only images, and it would still generate a dictionary of words, which are objects and actions,
so the
and relationships and feelings and expectations and Now the word dictionary comes if you only show it videos of beach waves will be different than a thing that's more general purpose. But yeah. And part of it's intuitively obvious, and part of it, as soon as you go down the rabbit hole, it's like, well, there's lots of details. Like I'm not.
Yeah, but I didn't understand this before, and when you pointed that out or kind of talked around that made a lot more sense to me.
Yeah.
So.
Yeah, there's the easy falsification of you need more data to be smart is here, and anybody can do that.
I love that.
Right, and then the falsification of this is a little more complicated because again, like they see interesting patterns in brains and you go, what the hell's going on? But you look at LLM's thinking and some of the patterns you think, what the hell's going on? So some of that is currently mysterious. The fact that we don't know how humans train neural networks is awkward, even though the computation's on what they call the forward pass. When you do inference, so think about this, your brain does an inference in like 100 milliseconds. It goes through a lot of levels, but you can think about something for days. Mm-hmm. So how many cycles through the brain is it doing? And your brain has something that looks like a workspace and several levels of it. And it has something like mixture of experts. Your brain technically is partitioned into lots of pieces. It's very good at coordinating those, but also running cycles independently on it. But we don't know exactly how that works because the brain, when you look at the cerebral cortex, looks crazy uniform. Sorry. So.
You also pointed out something that was kind of an insight when you did the tree diagram and the element of surprise. And at the bottom of the tree, if we find out we did a calculation wrong, we don't mind making the fix. But the further up it goes, the harder it is to fix. And it's it reminds me like the world is flat. I have all these, I'm really deep into the tree to believe that the world is round.
Yeah.
Now all of a sudden somebody tells me the world is flat.
Yep.
That's a very big surprise because I have to invalidate everything all the way up the tree and everything I've ever believed pretty much to the top.
Yeah, it's one of the problems with physics is people go, I take the Big Bang inflation equal mc squared for granted, and holy cow, But there's books for it. Thomas Kuhn's Structure of Scientific Revolution is a great book. Paul Feyerabend's book Against Method is even better. But you have to read. You should know something about science. Like Feyerabend's book works really well if you've read Kuhn already and kind of got it. And in there he calls anomaly surprise. But surprise is the moment where the anomaly comes in your consciousness as a serious thing that you have to do something about.
Yeah.
Like there's probably a technical form for that, but
And the bigger the surprise, the further up the tree
yeah.
you made a mistake
Yeah.
that you have to grapple.
Well, there's some times where the tree depth is interesting, and some of it's sort of like which way do I jump when I see a wolf? That tree depth might be really small, but but very impactful. So
It can also be hard to know where on that tree there's like an error in your previous thinking, or to even be aware of the content of the tree.
yeah,
Like
yeah, and also we're so effective when we're running this trained inference. Like I get why physics guys go, I don't want to reconsider all this stuff because I can crank out these calculations and build particle colliders and direct gravity waves. Like it's beautiful. Like I get it.
Humans also had this, you say we don't know how humans train, but we know a part of it, of course, that when a computer's training, you get a start date right now, and it starts completely from noise and then starts training. But when humans train, we have a whole history of how the humans behind us have been trained, and those are the training cues they've already found. They've already found weights, whether they're right or wrong or the optimal ones, or they found ones that work, and they build a system for us. So much faster to have those weights given to you than to try to figure them out by investigation yourself. Even if they're wrong, so much faster.
Yeah. Your pursuit towards the goal you think can be done is way faster than one you're not sure.
Yeah.
Right. And so there's a reason, but there's on the flip side in game theory, like the obvious thing is to always do everything that's already been proven successful. The problem with that is every once in a while a meteor hits the Earth and you have to do something different.
Yeah.
And then the problem is you only technically need 0.1% of the population ready to change your mind, but they can't change 99%. Yeah. So the human population is way more open to change than it should be because that's required because otherwise it couldn't change at all. So the game theory solution isn't how many people you need to be able to change. It's how many people need to be changeable to take a change.
Yeah. To affect one.
In
Right.
the movie Ready Player One, there was a character who succeeded by going exactly against what the game theory said to do.
Yeah. The inverse Kramer of game theory. Yeah, because the universe is overly indexed on game theory, and sometimes. So do you know how deer work? So deer jump in front of cars, and you think, what are they, crazy? No, they're not. They co-evolved with wolves, which are smarter. The wolves predict which way the deers are going to jump. So the deers jump in random directions sometimes, because that's the only way to outsmart intelligence. Yeah, that's a really great.
I love that because it literally was reverse. It's like,
Yeah.
oh my God, we always get crushed by King Kong here. What if I just go backwards through the course?
Yeah. What if? Yeah.
It just wasn't.
Yeah.
so much considered.
Which again is in game theory. That's just the meta level of game theory.
Yeah.
So it's cool. All right.
Cool.
All right. Thanks.
Cool. Hey.
Thank you. That's cool.